Welcome everyone. I'm Soohyuk CHO, and I'm an incoming freshman at University of California, Berkeley campus. And I'm currently planning to double major in computer science and astrophysics for my future and do some like computational astronomy research during my undergrad and going to grad school. Today I'm going to just talk about intro to gravitational wave astronomy, which is the one of the hottest fields in the 21st century. But before we start, there would not be like much like advanced physics knowledge that you might require. I just use some of the Einstein's equations to help you understand the physical relationship between the physical measures and the characteristics of the gravitational waves, but I will explain it in context. So when I just picked this topic for this research forum, I just wanted to give you an opportunity to understand why everyone is aspired to the gravitational wave astronomy research, so that like you can understand the history and technological development that scientists made to detect the gravitational wave in 2015. It is really important that you understand the historical background, because like a lot of people might have heard of like gravitational wave astronomy, open the new era of the astronomy, but they don't know what is the actual significance of this research field. So today I'm gonna overly talk about the history and detection technology development and significance of gravitational wave research. So on September 14, 2015, the twin laser interferometer gravitational wave called LIGO in Louisiana and Washington detected for the first time the gravitational waves in the human history. Gravitational waves actually got predicted by Albert Einstein more than 800 years ago. And it is also one of the secrets that modern astrophysics couldn't solve till 2015 before LIGO completely detected it. The LIGO team got the Nobel Prize in Physics 2017 for their achievements in decisive contributions to the LIGO detector and the observation of gravitational waves. And a lot of astrophysicists and physicists conclude that it was going to open a whole new generation of modern astronomy. Gravitational waves are the fluctuations generated by accelerated mass in the curvature of the space-time gravitational field, which propagates the speed of light. So astrophysicists have been attempting efforts to prove the existence of gravitational waves for more than 50 years, since Einstein's first predictions made more than 100 years ago. Numerous large-scale projects have been carried out to build a global gravitational wave detector for the direct experimental detection of gravitational waves. So what is the reason that astrophysicists are obsessed with the study of the gravitational wave? It's because it is the key to the development of astronomy. Because the gravitational wave is important since it gives humans the access to space in a completely different way and a wider view. Before, when observing the universe, we could study the history of the universe by using only light or electromagnetic waves through our like microscope and what do you call that, Hubble telescope things. But now we can discover new celestial bodies and make a research about it through our gravitational waves. With light only, it's really impossible to observe a black hole. But like even though we got a picture of the black hole just like very recently. So the observation of the gravitational wave results also can help us understand how gravity really works, the fundamental force that rules all this planet. The highlight of discovery is the also theory of everything, which is highly related to the string theory, which is considered as one of the most influential theory about the beginning of the space. So that now we can add the gravitational wave to the incomplete theory to create a whole model that encompasses all of the fundamental forces and particles on the natural world. So today I'm going to talk about the history of over 100 years of gravitational wave research, which is frustration and amount of money, and how we finally allow scientists the ability to take our first step to the complete merge of the standard model and the quantum model, and finally the theory of everything. So like before we start and delve into the historical context, let's talk about the physical fundamentals of the gravitational wave. So gravitational wave is a type of wave which transmits energy delivered by an accelerating mass of materials, regardless what material it is. So this is a wave that propagates in space-time, similar to the wave of the lake with a stone. It's cast on a calm surface. So it just makes a curvature in the flat surface. Gravitational wave is a concept that actually didn't exist in the framework of Newtonian gravity theory. So it is theoretically predicted from Einstein's field equation and his theory of general relativity, which indicates the degree to which gravity changes as matter changes in space-time. So this wave equation describes the gravitational wave propagated by the change of gravity caused by the certain change of motion of a matter. According to Einstein's theory of general relativity, gravity is the fabric of the universe, which means the larger the mass of the celestial body is, the more distortion mediates the time and space around it, like the figure 1. There is a curvature around the Earth where the gravitational wave is like mediated. Thus, the heavenly body makes the objects around fall toward it, which is like black hole of the space. When the mass of an accelerating object is large enough, it can generate detectable gravitational waves or ripples in space-time. Since this curvature is mainly generated by the mass, the curvature of time and space also fluctuates when an object has mass accelerating in any space-time, regardless of distance, because the gravitational wave can travel the whole universe. So when an object with mass accelerates, the curvature of space-time propagates in the form of waves, which are called gravitational waves simply. So a typical example of system that emits gravitational wave is a white dwarf system, which is a really, really heavy celestial body. Or like a dual binary system of the black holes, which includes a neutron star or a black hole. So that there are two heavenly bodies, which is really close to each other. And while they are spinning and orbiting each other, at some point they just collide and become one huge celestial body. And when they collide, they just generate a huge intensity of gravitational waves. So given some simple mathematicals and assumptions and symmetry, we get important properties of gravitational waves. The first important property is, as shown here, is that the waves will propagate at the speed of light, as already mentioned. And the second one is gravitational wave has some rotating properties called polarization properties. So polarization refers to the oscillation in a specific direction with respect to the direction in which the waves actually propagate, which can be linked to a snake's body oscillating from side to side as it moves forward. So if you see the figure 2, you can see that there are two different polarization modes called plus polarization and cross polarization. So the first line is the plus polarization, which means that a plane perpendicular to the direction of gravitational wave vibrates repeatedly in contraction and expansion, I mean. So, and the second one, the cross polarization, as it states, means the cross polarization occurs as it is tilted at 45 degrees. So if you see the period of pi over 2 and 3 pi over 2, you can see it is tilted on the plus polarization, which is very perpendicular to our horizontal line. So the wave represented by this wave equation oscillates in a direction perpendicular to its traveling direction, alternately in a plane as shown here. So this is called the quadruple polarization of gravitational waves. So it is often compared to an electromagnetic wave, which is also another very influential wave of our space-time. And the biggest difference is the electromagnetic waves are waves generated when a charged material accelerates. And its generation is actually same as that of gravitational waves. The difference is electromagnetic waves only have one polarization called dipole-dipole interactions. So a material with a mass is always subject to gravitational forces, even you guys, humans. And when this material accelerates, it always generates gravitational waves, even though it is very weak to detect without professional detection technology. So the other feature of gravitational wave is its intensity. So let's try a simple calculation, assuming that the two objects with a mass of 1 ton each are rotating about 1,000 times per second at a distance of 2 meters. So it sounds really huge, right? But in this case, the intensity of gravitational wave, these two binary systems generate is only about like 9 times 10 power minus 39, which is literally negligible. Therefore, it can be said that intensity of the gravitational wave due to the accelerating motion occurring in our daily life is very little, so that we could not feel that. We calculate the strength of the gravitational wave is measured how much the length of a material is changed by the gravitational waves. I'm gonna explain it more when I talk about the LIGO algorithms and detection technology features. So if you see the equation, like H is equal with the delta L over L, where L means the length and delta L means the change in the length. So that is when a gravitational wave passes through an object having a certain length, the space-time vibrational motion represents shrinkage and expansion time to the time according to the vibration mode of the gravitational wave. So we define the intensity as the ratio of the length variation caused by the oscillatory motion and divided by the original length, as I mentioned. So let's talk about the first history of the theory of gravitational relativity. So Einstein was the first one who actually theoretically considered the existence of the gravitational wave through the point of view of quantum mechanical system and general relativity. So before gravitational wave appeared in the world of physics, the classical understanding of gravity was first made by and ruled by the Newtonian gravity system. Isaac Newton, who analyzed the astronomical observations and theories that were considered to be the most intellectual disciplines at the time, found that the force between the two objects is really related to the mass and distance between the objects. And he also succeeded in expressing the nature of the intensity of that force is proportional to the product of the masses of the two objects and is inversely proportional to the square of the distance as a mathematical equation, which is very well known, F equals G m1 m2 over r squared, which is called Newton's law of universal gravitation. So this formula is still valid for describing the motion of an object in a weak gravitational field, even in the new concept of gravity theory described by Albert Einstein. But although Newton's theory of gravity explains the astronomical movement with astonishing success, it still fails to answer the essence of the force. So for example, in Newton's view, all objects exert a force that attracts other objects, which universal law of gravitation works pretty well. But according to his perception, we cannot explain Mercury's peculiar orbit, which is really close to the sun. The orbits of planets shift over time and time, and Mercury's orbit shifted faster than Newton predicted. So let's talk about what Einstein actually did. Although he found, Newton found the exact laws of interactions and movements of the celestial bodies and all the materials and masses subject to the gravity, it could not provide really a clear answer, and that's why Einstein came up with the theory of general and special relativity. So the special theory of relativity suggests that the state of motion of an object based on the principle of constant velocity of the light cannot ever exceed the speed of light. So the maximum speed the search object can reach is just the speed of light. This way is actually explains the opposite of Newton's idea of describing existing gravity. So according to the picture, Newton thought that gravity would act immediately without allowing any time difference for objects, so that objects cannot feel any gravitational forces on themselves, because he considered the surface that gravitational wave and forces interact is really very fixed and flat. But in other words, on the other hand, Einstein's theory of relativity considers gravitational waves is actually not a force, but accelerating motion itself, so that it creates the time and space curvature, as you see here as flexible space-time. So Newton's theory of gravity predicted that after the sun disappeared, for example, we would immediately not be able to see the sunlight in our sky due to the instantaneous effect from gravity. We cannot feel the gravity is actually working between our sun and our planet, the Earth. But however, according to the Einstein's theory, we actually would still be able to see the sunlight for 8 minutes, even though the sun disappeared before. It is just simply because the light takes roughly 8 minutes to move from the sun to the earth. So unlike Newton's concept of gravity, Einstein tried to use force to explain his bizarre phenomenon and thought that the essence of gravity is the same as the acceleration movement of the object. So we call this as an equivalence principle, the basic fundamentals of general relativity, which is the motion of an object that receives gravity in the gravitational field cannot be distinguished from the object that performs acceleration. So we consider the movement in the gravitational wave and the change in potential is exactly identical to the classical mechanical view of accelerating motion. So the concept of force is not the cause of the movement any longer, but rather the movement itself that occurs between objects with masses. So based on this, through general relativity theory, Einstein predicted that when a massive material accelerates, the change appears as a whole wobble of space-time, and eventually its energy, the change space-time, is propagated like a wave. This is what we call the gravitational wave, simply. So Einstein describes his wave equation propagated with the solution of the wave equation. And based on his first field equation, to find the field anywhere through the perspective of the Newtonian mechanics, we use the equation on the left. You might not understand this like right now, but the left side is the gravitational potential and its second derivative, and the right side is some kind of constant, including gravitational constant, and times its mass density. So what it explains is the second derivative of the gravitational potential is directly proportional to the mass density. So this is one of the generalization that Einstein made for his general relativity theory. So in the right-hand side of the Newtonian field equation should have the mass as a form of the rest energy, and the momentum and energy should be equivalent. And also to generalize this, the left-hand side, which is the second derivative of the potential, should be generalized into the relativistic gravitational potential. And to generalize in the form of identical momentum energy system, we use what we call tensor. So the left side is relativistic gravitational potential, and K is what we call Gaussian curvature, which is generalized as a tensor form. And T is equal with the energy momentum tensor. So we just convert all of those like physical quantities into what we call tensors to explain more multi-dimensional systems. So this kind of concludes that how the energy momentum tensor is related to the curvature of space-time and how much it brings. So it seems like Einstein is a pioneer in this field, but even himself thought the gravitational wave doesn't exist at the first time. On the paper he published in 1916, he thought gravitational wave is like actually does not exist because it was really extremely weak and mathematically awkward. So after Einstein made his first step on the theoretical aspect of the gravitational wave research, the first one who tried to make some experimental research was Joseph Weber, an American physicist, and who made the first gravitational wave detector called Weber bar. So he actually brought a huge wave of the gravitational wave research paper and the technological development in this field. When he visited the Caltech in 1957 as a research fellow, he published a paper on gravitational wave detection with prominent relativist John Wheeler. So he discussed the model of theoretical properties of gravitational waves with cylindrical symmetry, which is like the bar on the left bottom side, which is called the Weber bar. So he proposed an experimental methodology for measuring gravitational waves, which used the fact that physical change in the crystal structure of an object can be generated by the second order differential form of the gravitational field, which is the subject to the Einstein's field equation. And after he returned to his home Maryland, he produced a room temperature resonance bar detector called Weber bar, which is the prototype of the experimental gravitational wave detector. And this device was a cylindrical aluminum bar detector with a sensitivity of about 10 power of minus 16 at the resonance frequency of around like 1000 some hertz. And he maintained it for about 2 years, and he caught like 10 signal candidates and submitted the results to the physical review. For those candidate signals, Weber concluded carefully these ordered signals are not completely ruled out due to the effect of the gravitational wave. So he was really careful to conclude that it was actually a gravitational wave at first, but because he speculated that it might be a signal due to a problem with detection calibration or like some noise or like a pulsar caused by other celestial bodies. But after the following year, Weber finally submitted a paper analyzing the coincident events of the signals from two bar detectors that were operating at about 2 kilometers from each other. So the research result that Weber got was identical, even for the different time and spaces. Weber then presented the probability and frequency of coincidence for each signal, and also there were also candidates for which one of those signals was only every 8,000 years. So he thought it was a coincident one. This is like actually the proof of the detection of gravitational wave he made, and that's why Weber had 4 room temperature resonance bar detectors until 1969 and just keep working on detecting the gravitational wave. And he believed that he had found himself more gravitationally, and since the announcement he made, he has created a group of gravitational wave detection experiments in more than 10 places around the world. But there was a problem. The theoretical physicists, on the other hand, began to explain what causes Weber's gravitational wave signals. So these 3 physicists are Stephen Hawking and Gary Gibson and Richard Garwin each. And all of these 3 physicists were like very skeptical about Weber's experimental results. Hawking and Gibson have studied the models that gravitational wave sources can have in a view that the sensitivity of the bar detector based on Weber's argument, and they calculated the energy lost by emitting gravitational waves based on Weber's claim, and they found the calculation results that the gravitational waves come from our galaxy with that energy. After it is emitted, our galaxy cannot be even maintained. So it was kind of very mathematically irrational. And they also made intensive counter arguments. In addition to that, there were reports of suspected problem errors in detector collaboration made by Garwin, because he considered that actually this generated signal really looks like that one, the gravitational waves produced from some proper combinations in a number of complex noise files. So he just considered that Weber intentionally changed the data so that it seems like really rational and identical to the gravitational waves. So he has actually failed to detect the gravitational wave, but this unsuccessfulness rather gave other scientists hints at the development of technology, which is only for the gravitational wave. So the beginning of the generation of laser interferometers started right after Weber's failure. So the styrogenic bar detector had a sensitivity of 10 power minus 19 in the resonance frequency, so that this frequency range that the Weber bar could like detect with the gravitational wave is very narrow, which is a dispute that the era of the bar detector is one that declined. So scientists started to think of a new way to make more effective and more sensitive gravitational wave detectors for the detection technology. And the first one they tried was a spherical detectors. One of the advantages of the spherical detectors is that they could respond to the 5 different sets of colorful polarization modes, which means it is still more sensitive than the bar detector. So in the United States, Louisiana group, the first spherical detector project has begun, called truncated icosahedral gravitational wave antenna, which is abbreviated as TIGA. And also in Netherlands, the other gravitational radiation antenna called the mini-grav detectors, constructed in Leiden University to test the prototype of the gravitational waves. So the left side, which looks like really a soccer ball, is a TIGA, and the right side, which is more like flat spherical one, is a mini-grav. So this was a spherical body composed of 32 flat pieces, and of 20 hexagons and 12 pentagons, and was a device that showed a sensitivity of 10 power of minus 11, which is better than the Parse detectors at a resonance frequency. And resulting from the appearance of the LIGO, however, actually this project is the United States pushed it ahead with, and it could not be accomplished in earnest. So after this try even failed, the scientists think of a new perspective to how to detect a gravitational wave. So before that, they just only consider the change in the length of in the resonance frequency of a very small bar detector or like spherical detectors. But now they started to think of like make a really huge detector so that they can easily analyze the change in the length caused by the gravitational waves. And that concept of detector they thought was a Michael's interferometer. So one of the biggest contributors to this project is Keith Thorne, the astrophysicist at California Institute of Technology. He was the first person who analyzed the conditions that the laser interferometer should have for gravitational wave detection and noise sources of the interferometer. And he also built and experimented with various prototype interferometers ranging from several meters to hundreds of meters. So another important contribution he made is he studied the possible astrophysical wave sources model for the detection frequency bandwidth by using the Michael's interferometer. And he proposed a theoretical background of gravitational sources emitted from the high neutron stars and black hole binaries and the sensitivity of detectors for the detections. And he was also interested in improving techniques for the gravitational detectors. So he involved in the discussion and research to explore various possibilities through interactions with a number of physicists from the beginning. So the left side picture is the basic algorithm and the structure of the Michael's interferometer. When the laser starts from the laser pointer here, it goes through the mirror in the center, and it got reflected from the mirror on the right. And after that, it is reflected so that it could go to the mirror of the upper side and going back to the screen. So basically, it counts how long those light travels from laser pointer to the screen, and it can easily help us to detect gravitational waves because when the gravitational wave affects to the movement of the light, the time that light travels would gonna be shorter than the original because gravitational wave would gonna squeeze and make a curvature in our space time. So this is the picture of the LIGO. So if you see this, they have like two arms with the 4 kilometer each to make a precise analysis and experiment for the detections. And in 1917, a LIGO project finally proposed, and with the approval of the United States government, it is built in 2 different regions, one in the Livingston and one in the Washington. So Caltech and MIT, and with famous professor Wallace Weber and Keith Thorne, was responsible for the project at the first time. And the name for the detector was officially proposed as LIGO, and its report was produced and submitted first on the 1999. Since the construction was approved in 1991, LIGO continued to operate in a scientifically meaningful observation mode until the 6th scientific operation. And there was another huge contributor called Virgo. So Virgo is a European version of LIGO, which is built by a French-Italian joint venture and their government. So the scientists worked on 2 LIGOs and 1 Virgos all around the world, and they still couldn't get enough data which can help them conclude that mathematically and physically the gravitational wave is actually exists. So LIGO just go to the 5 years of upgrade. And finally, on October 21, LIGO went into the assembly process and went to the upgrade. And after 5 years of it, LIGO finally detected gravitational wave from 2 different binary systems. And it was a really huge step for the gravitational wave astronomy because this detection opened a new era for the global gravitational wave network and next generation detectors. So, for example, there are still other countries working on building the new generator and detector. For example, Japan is currently building the um, gravitational wave detector called Kagra in their country, so that we can literally detect the gravitational waves all around the world, Asia, Europe, and North America. And there is also LIGO India project is going on, but I believe it's not built yet. But it from this we can expect that our gravitational wave research network is currently more and more expanding to worldwide view. And by using the very parrot resonator, the scientists are thinking of sending the gravitational wave in the space so that we can more clearly detect the gravitational waves. So this one is called ELISA. So it's really similar to the LIGO, but it has 3 arms instead of 2 arms. So there are 3 detection points, and they are connected with the arms here so that they can make a triangle. And the European Space Agency is trying to send them in the universe because in the Earth, because of the gravitational fields that Earth and the solar system create, sometimes the gravitational wave that travels from a really further Earth and other galaxies got interfered by our Earth's gravitational field. So they expect that this ELISA development will help us detect the exploration of gravitational wave from more mass black holes that we could not find in our galaxy. And there is also a technology called pulsar timing. And if we use it, seems okay. So the right bottom side is called pulsar timing. So we just send the detectors in a certain space-time area, and we get the pulsar of each one of these devices so that we can conclude that whether timing is identical. So this will gonna prove more precision to our detection technology in the future, and it will literally help us to build more and more experimental systems for our detections. So I will gonna talk about the significance of this research because it's meaningless to know the history if you don't know the significance of research and what it could done. So the first one is we can now hear to the universe. So usually when you use the telescopes, you can only see and watch the universe. But here means you can get a new perspective and new approaches to the celestial bodies. So if we get the enough technologies to generate the gravitational waves in the future, it is gonna immensely help us to detect further celestial bodies, like a black hole discovered in 2019, like this picture shows. And another one I believe is really important is called the theory of everything. So if you see the lab table, this is the structure of a modern physics theory. And I think some of you might know what is the standard model of particle physics and standard model of cosmology. So this is still 2 different distinguished methods. There are 4 fundamental forces in this universe: strong forces and weak forces, electromagnetic forces, and gravitational wave forces. But the current problem of the modern physics is the standard model of particle physics only consider the 3 particles, which is strong, weak, and electromagnetic particles. And the standard model of cosmology only uses the gravitations. So which means we cannot conclude that all of these fundamental particles are identical and exchangeable. And what unifies these two different theories is what we call the theory of everything. We call this sometimes final theory, ultimate theory, or master theory because it's hypothetical single framework of physics that can fully explain and links together all physics aspects of the universe, regardless of using Newtonian physics and great general relativity or quantum mechanics, because this theory assumes that all of the 3 would going to be unified and have a certain single point of framework in the physics. And it is also really related to the string theory, which is very famous now, that universe is not just a space-time, but rather a multi-dimensional string. So the problem of the string theory is that it is mathematically reasonable and there is no errors regarding it. But the problem is there is no way to experimentally detect or like conclude that string theory actually can prove things. So if we send like ELISA to the space and keep our like detection technology things, the scientists are planning and expecting that they might be able to find the gravitational waves from a era near the beginning of our universe so that we can understand the origin where we are from, which is really important. And the last one is the graviton and black hole research. Graviton is the particle which actually mediates the gravitational wave. And it is important because it's also one of the 4 fundamental particles that can be included in the theory of everything. And if you guys saw the Interstellar, you can see that in the movie, in the last part, you can see the spaceship that Cooper drives just keep orbiting certain planet and use a swing by system so that they can go to further universe with less fuel. So if we could like create the gravitational wave technology and combine it with our aerospace engineering technology, that swing by technology will lead us to the era of the universe exploration. And for the black hole things, actually what LIGO did is like only detected like 2 small black hole binary system and the gravitational wave it actually generates. So the smaller black holes detected by LIGO probably formed from the stars that lived close together and stayed together after death and eventually spiraled towards each other and merged. Then we can just get a lot of questions about this. How many black holes from in cluster and how many from outside cluster, or how many black hole merges take place in the universe each day? How big do these black holes get? So these are the questions that scientists now have a better shot at answering because they can detect black hole merges directly by using the gravitational wave, which we couldn't with the light because black hole actually eliminates the light due to its like high gravitations. And we can quickly figure out the exact masses of those black holes. So all of this research was just the beginning. LIGO detected to confirm the black hole mergers in the first science run, which lasted only about 6 months. Currently, LIGO is kept operating at only about 40% of the sensitivity it was designed to take place. And gradual improvements by the LIGO team will slowly drive the percentage up and which bump in sensitivity. Meanwhile, a companion gravitational wave detector is scheduled to go online in Italy, Japan, and India this year. So LIGO's discovery means a lot of things to the astrophysics community because it might really actually be the beginning of a new era. Yep. Thank you for your listening. And are there any questions?